Hey, good morning. So first, I wanna give a shout out to Caitlin Moore back there, who's my co-founder at Devonian Systems. And what we are doing in collaboration with a bunch of people in this room, including the amazing team at Gainforest, are building what we think of as a global operating system for nature. And so you might ask, like, what is this? And like, why does nature need something like a global operating system, right? And so this is a place I've spent sort of a lot of my career is in just technological development and scientific development of various different technologies. And when you look at so I did a lot of work on solar cells and batteries, and so like physical, like materials oriented systems that have real, have like push atoms around in the real world. And when you look at a bunch of these physical systems and also some things like cash cards and ATMs, right, that are more like human innovations. First thing to notice about this graph is they take decades to go from R&D and sort of the initial sort of stages of an idea to something that's actually implemented at scale, having real impact in society. The second thing is that's interesting about this like visualization in particular is that the blue bar is research and the yellow bar is implementation, right? And so in this model, right, in this like typical way that we think about coming up with new ideas and those ideas having impact in the world, there's a research phase and then there's a implementation and scale phase, and they are separate, right? You like figure out what you're doing and then you do it. And the problem is we don't have time to figure out what we're doing and then do it. Right. So this is news from the past 2 weeks, right? So there were these horrible floods that Max also mentioned in Spain, south of Barcelona. This is from the emissions gap report that came out, I think October 24th, something like that, from the UN environmental program. What you want to kind of focus on here is this like 66% chance number, right? So we're at I think this year is on track to be like 1.55 degrees Celsius above the pre-industrial average. So that's like a lot of warming. I was watching Chasing Ice a while ago, and so this documentary came out about global warming, 10 years ago or so, and they're like, it's so bad, we're at 0.8 degrees above global warming, and like all this stuff is happening. I'm like, wow, those are really rookie numbers, unfortunately. It's not good. So, so by the end of the century, right, with current policies, so that's like what we were on track to do before the US election that was already signed into law, right? We're on track for 3.1 degrees of warming above pre-industrial levels. If you actually pay attention to naturally determined contributions, which countries have said to the UN that they're gonna do to decarbonize, but haven't actually signed into law yet, you get to 2.8, 2.6. And then if you actually make net zero pledges, which everyone's really far away from doing, you get to 1.9 degrees of warming above pre-industrial levels. So the point is here, like we don't have time we have to build the plane while we fly it, right? We need to like learn about these systems, learn about interventions, and implement those interventions in parallel with each other. And so that's why we need a global operating system for science. One of the things that we need to be able to do as we're like building this electric plane, as we're flying it, is we need to be able to rerun the numbers quickly and efficiently, and our current information systems for science are not set up to do that. This is one of the studies that led to this famous Guardian article that sort of blasted carbon markets to shreds in early 2023. And essentially what they did was they said, okay, typically when you want credit for preventing deforestation, what you do is you specify your project area, you specify a baseline area, and the more deforestation there is in that baseline area, the more credits you get. The implication is like we prevented deforestation that would otherwise happen. And what they did is they just came up with this idea of a synthetic baseline. So they said, okay, rather than allowing the project developer to specify what they want to be what they want the control to be, let them kind of like write their own test. Let's just like run some stats and like rerun these numbers on these projects, right? So the point is though, if we had a global operating system for science, it wouldn't take like years and decades to like figure this out and actually do this research. If we use the tools that we have to make science interconnected, and then connect that to the actual implementation of those scientific ideas, we just create an entire pipeline where we can just rerun these numbers whenever we want to, and really accelerate our ability to course correct for problems in what we're doing now, right? We learn faster, implement faster, and solve the carbon and biodiversity crises. Why doesn't open science, the way it exists now, like solve this problem, right? So there are what are called FAIR principles, so findable, accessible, interoperable, reusable. That's sort of this set of principles for the open science movement. That's important. If we're gonna have open data and open science, we need data sets to be, quote, fair. But when the open science movement started implementing a lot of these FAIR principles and said, okay, let's just like open data, let's have, kind of have this free-for-all, let's let everyone look at the data, look at the code for what we're doing, and that's gonna like accelerate science. The problem is like, there's actually, especially in this area, especially when you're dealing with indigenous people and local communities who are deeply connected to this land, you also need these care principles, right? You can't just like open up all of this data that is like deeply meaningful to a lot of the ecosystems and people living in these ecosystems that you are working with. You actually like need to give them sovereignty over what that data is, how it's shared, how they're compensated for that data, what's done with that data, and bring them in as stakeholders into this, right? And so we actually need more fine-grained control than the typical sort of like Zenodo-style open science movement gives us. And so this is like one of the areas where the tools that we're working with can really like make a huge impact in this problem. So what are some of the tools? I've talked about this before. You might have heard it, but we can really think of hashes and CIDs as a universal coordinate system for human knowledge, right? So the point here is that CIDs, right? So addressing data based on its content rather than its location, are this like incredibly massively powerful concept that we're only beginning to see the implications of. People have known for a long time about data structures where you use hashes to prove that your data is included in some larger data structure. So like a Merkle tree, right, you're able to efficiently use hashing to prove that this little chunk of data exists in the context of this larger structure. So that's great. So lots of people for many decades have said, hey, if I hash my content, I can efficiently verify my data in the context of this specific data structure. And that's great. We've known about this since the 70s. It's all works really well. It's really good. But the core sort of realization about content addressing in Web3 is that hashes are incredibly overpowered for this particular use case. So Web3 says, hey, if I hash my content, I can efficiently verify my data in the context of all of the data, every data structure ever, right? You're not just verifying that this chunk exists is like the chunk you're looking for in the context of this Merkle tree. You're showing like this is the only data in the universe, within reasonable assumptions about collisions, that satisfies, these requirements, right? So that's a big deal. So Churty, if you go to churty.io, Churty is a global operating system for science. And this is what Churty looks like. So the way to think about this is a simple example, and we're gonna kind of use this really simple example to talk about the set of concepts behind Churty. Please come to a workshop later if you want to talk more about how to sort of apply this to more complicated examples. But so you should think of this as a pipeline, a data pipeline, where these lines are data sets, and these boxes are functions or data transformations, and data flows from left to right. And so if you click on this, select this, this is the data that like fills that position in that Churty graph, right? So this is a image taken by Oceanus in collaboration with Gainforest, looking at mangrove trees in the Philippines. And so then this box, right, is this machine learning model that is optimized for delineating tree crowns. Sorry, did I just say tree crowns? Tree crowns in mangrove forests, right? So you plug in this image to this ML model, and what you get out is this delineation of, it shows you where the trees are, right? And so this is the input image, this is the output image, just to like make that really clear. And so this is a data pipeline in Churdy with some really important, relevant features for all the motivation we were just talking about. So, one thing you might ask is, okay, how do you actually build a graph like this? How do you use Churdy to build this pipeline? Well, so we support Python now. You can install something called PyChurdy, and then what you can do is you can take your script, which loads your data, runs it through this like ML model, and then you can import PyChurdy, and you can do what we call checkpointing data and code into this graph. So when you just like run this script, then this is gonna checkpoint the script itself along with metadata needed to rerun that script into this this like function here, which represents this data transformation. It's then going to, when you have a data set, you can then checkpoint that data set itself into this pipeline. And so that's sort of the workflow for like creating these graphs and filling them with data. But what's the actual like structure? Like what is in a Churdy graph? So a Churdy, the structure of Churdy combines this like mathematical thing called an operad, which is this like really beautiful mathematical like set of structures that come from this thing called category theory, which is the study of composition. And it combines that with essentially CIDs, right? So like IPFS and Filecoin. And so what are these like data objects, and what are data objects and like boxes, and like what does the graph I was just showing you mean in the context of the structure I was just talking about? So firstly, data objects themselves are content addressed, and they have this Git-like versioning system where you have versions, you have graphs, and every data structure itself is a blockchain. So it has this like the CID of the previous version, and it points to that, right? And then you like hash this thing and refer to it as in the next kind of version on the same branch, or you can have multiple different branches that all refer to previous. You get it. Then this pipeline itself has the structure of this thing called an operad, which essentially, like, you should just think of this as it's like this mathematically really sort of convenient way to think about how things depend on other things. And so when you have boxes here, boxes are hierarchical and composable. So there are these data transformations that you're able to specify what code corresponds to that data transformation, and then you're able to reconfigure them. So if you have this little like subgraph and it fits into this other subgraph, you can paste them together and you can extend your Churdy graph. And so an example of that might be like, if I have a company and I want to prove that my company is net zero, and I buy a carbon offset, hopefully a really high quality carbon offset, maybe that carbon offset already has a bunch of data as a Churdy graph, right? So they've like collected a bunch of data showing the forests that they're protecting. They've done a really good job. If I want to make a net zero statement, preserving all of the work that I'm building on top of, right? Preserving all of the work that this like carbon offset project did, that my net zero claim is based on. Like the mathematical structure of operads lets me like prove that without data loss, right? That's kind of the point. It's like you can take different things, and if they fit together, they like fit together well. So boxes are this like hierarchical composable structure. Then, so like this, you select one of these data objects, and you can fill this position in the Churdy graph with data, with like that data object. And so, maybe this data object is this like input image. Maybe this thing on another branch, or maybe it's a totally different data object that like doesn't share branches or versions, can go into this like slot in that graph. And then when you checkpoint data by running this code into this Churdy graph, that's what you're doing. Is your checkpointing produces a new version of every data object, every box, and like the pipeline itself. So everything has a CID, so everything is kind of nailed down in this universal coordinate system for knowledge, but you preserve this notion of composability, so you can take things that kind of fit together and glue them together without losing data. So that's kind of what and why. What is this? Oh yeah, so this is like how you actually do this, right? So this is a JavaScript package that lets you create and work with data pipelines and data objects according to this protocol, right? So there are functions in here for creating a new pipeline that doesn't have anything in it. There are functions here for adding a new box, changing the connectivity between boxes, adding data, like filling, one of these like positions, like this like image position in this graph with a new data object, creating data objects, interfacing with storage that's modular, so you can like create your own storage system, and this will like automatically make sure that you don't lose CIDs when you create new hierarchical structures in this this whole graph. So that's this thing. Popular ESM is a way to do that. And then so we've talked about kind of what and how. So now we can talk about why, right? Like, why does that motivation that I talked about at the beginning actually like fit well into this structure, and why do we need this notion of operads combined with this notion of content addresses to actually like accomplish those goals? And so, oh yeah, this is what I just said. Yeah, what's the value of combining these? That one. So one of the reasons is that when we have this strong notion of composition and dependency, we know mathematically what depends on what else. And what that means is that if you have a input and you have some code and you trust the input because you have data provenance saying that I trust this input, and you trust this code because you have data provenance showing that you trust the code and you trust who ran it, or you have some proof showing that it was executed correctly, then you should trust the output, right? We know this depends on this. We get that from this structure of operads, so we can just calculate really straightforwardly whether or not we trust this thing. We can like overlay this data provenance on top of this structure and determine whether we actually have a good reason to trust this data that we're getting out. So that's really important for making decisions in the real world based on some set of data, right? So that's one reason this structure is useful. Another reason, oh yeah, and so an alternative would be maybe I trust this, maybe I still trust this. Oh hey, that works better. Maybe I still trust this input data, but I don't trust this code. Then I don't trust the thing that depends on that code and that input data, right? If there's like some link in this chain that I don't trust, then I don't trust the output. So then also coming back to this notion of why don't existing tools in open science sort of solve this, right? Because we have this same strong notion of composition, that means we can give credit for and compensation to the people who provided this data and code. So if we want to make sure that people are adequately compensated for, say, providing training data that then produces a machine learning model that then I am using to make my like net zero statements, and that's very valuable. In current systems, there's no kind of way to check and make sure how much were these people compensated who collected that data, and did they like give their consent to use this data? But again, because we have this like strong notion of composition, we can again calculate. We can either say, okay, who provided this, and we can use provenance to figure out do they actually give their consent, or we can, if they say, okay, I want to charge for my data, or I want to charge for my code. Again, when we rerun this graph, we can just calculate what is the cost to rerun this graph and make sure that money actually goes to the people who provided that code and data. Then the sort of last piece here is then, because you have this composition from this mathematical structure and also immutability from CIDs, that makes these different pieces interoperable. So you can like rerun these things more easily than you could otherwise, because everything is glued together by these two structures, right? You have this like operad structure which just ensures that everything is kind of works together, and then you have CIDs which like nail down your data structures. That means you can take this thing and swap it out with this thing, and then hopefully be able to rerun analyses like this much more easily than you could if everything doesn't. In the current system, it's really hard. Like, I don't know how many people here have like tried to take an academic paper and just like download the data and download the code and like redo the analysis. It's very difficult and very frustrating, and a structure like this lets you do that more easily. And then sort of less sort of thought here is, so what happens when you apply this universal coordinate system for data to the web of human knowledge? And the answer to that is you reveal this like true underlying structure, right? So we're all working together to understand natural systems better and try to solve these problems. So this like underlying connected structure really exists. Like it is a true thing that is out there in the world. But because we haven't taken this universal coordinate system for data and applied it to that structure, it's all fragmented, right? You can't access it frictionlessly or easily. And so I think what we're doing here is like trying to get closer to that true notion of all of us collectively trying to make progress on these issues together. So please come talk with us about any aspect of that. And we have a workshop in about 2 hours, a little less than 2 hours, that Caitlin's running, and I'll be there too. And please come talk. Thanks. Questions? Any questions? Maybe questions? Some questions? Oh, hey, how's it going? Sorry. Yeah. There are, so he was asking, can I use sort of any CID or any data structure as input? And yeah, it is built to be modular so that you can, like, ideally you want something that has a meme type so you actually like know what functions it fits into, but you could like build a non-standard meme type or just like try to run it and maybe it'll crash. But like it is built to be modular such that, yeah, you can take like different data structures or different formats. It's really optimized for like machine learning models dealing with visual data is like what we've done sort of the most work for it on. But also like bioacoustic data, like we're thinking a lot about kind of nature tech.
Questions? Where are you guys storing this data and how you prevent it from just being hacked?
Yeah. Well, so it's built to be modular such that you just need a CID, and so you can drop in. So like that popular ESM thing, like you provide it a storage function and you provide it a retrieval function, and then you can just like handle that however you want. So you could just connect it directly to IPFS. You could connect it to your own server that like content addresses data, but controls permissions, or just handle it sort of however you want. The point of this is to be sort of a layer on the stack that like gives you that interoperability and sort of nails things down with CIDs, but then lets you sort of manage permissions on top of that.
All right. Thank you so much.
Cheers.
Got to get to the next talk, but you'll be able to find Alan in the workshop space.